Okay, our discussion is on moving loads. So from our previous discussion in the previous section, we were able to identify that maximum moment occurs at a point of zero shear. So for beams that is loaded with concentrated load, you have to take note that the point of zero shears usually occurs under a concentrated load, and so the maximum moment. So if we have a beam and girder, so an example to that is a bridge or an overhead crane that is subject to moving concentrated loads which are at fixed distance with each other. So the problem here is to determine the moment under each load when each load is in position to cause a maximum moment. So the largest value of this moment governs the design of the beam. So for our moving loads, so basically this is applicable, this concept is applicable to our beams and girders in a certain bridge. So wherein it is subjected to a moving concentrated load. So we are having to, in the design of that, we are going to identify the maximum moment under each load. So whatever is the maximum moment governs the design. So for a single moving load, the maximum moment occurs when the load is at the midspan, and the maximum shear occurs when the load is very near the support. So it usually assumed to lie over the support. So we have here an illustration for a moving load wherein you have your maximum moment, which is having an equivalent function equation PL all over 4, and you have your maximum shear, which is equivalent to P. For two moving loads, if there is a presence of two moving loads, so the maximum shear occurs at the reaction when the larger load is over the support. So meaning to say, if we're going to have two moving loads so that you could identify the maximum moment, you have to place your load that has a greater value on the support. So the maximum moment is given by, however, the maximum moment is given by this equation. We had quantity PL minus piece of SD, piece of S times D squared all over 4PL. So our piece of S here is the smaller load. Our piece of B is the bigger load. And to have the value for the total load, of course, that is piece of S plus piece of B. So for three or more moving load present on the beam, so in general, the concept here is that the bending moment under a particular load is a maximum when the center of the beam is midway between the load and the resultant of all the loads then on span. So using this rule, we compute the maximum moment under each load and use the biggest of the moment for the design. Usually, the biggest of this moment occur under the biggest load. So for this one, we have to identify that for us, if there will be three or more moving loads, we have to compute the maximum moment under each load. So each load, you have to compute the maximum moment. Then the biggest value of the maximum moment will govern on the design. So meaning to say that will be used on your design of that particular element of a certain structure. So the maximum shear occurs at the reaction where the resultant load is nearest. Usually it happens if the biggest load is over that support and as many as possible of the remaining loads are still on the span. Okay, for our first problem, we have a truck with axle load of 40 kilonewton and 60 kilonewton on a wheelbase of 5 meter rolls across a 10 meter span. Compute the maximum bending moment and the maximum shearing force. So for this one, for this example, this is our given figure. So we have here a load which is 40 kilonewton and 60 kilonewton. So we're going to identify of course, we have to identify our resultant R. So that resultant R has a distance of X from 60 kilonewton, and of course from 60 kilonewton it has a distance of from R towards this 40 kilonewtons. So since this is 5, so basically this one is 5 minus X. Okay, let us identify our reaction force. So our R here will be equal to 40 plus 60, and this gives us 100 kilonewton. Then for our X, we have to identify the value of our X. So to solve for X, let us have this as our reference point. This will be our reference point. So therefore, if we're going to have the value for X, so that will be X R times X. So resultant times X is equal to, we have 40 times the distance, which is moment arm distance, which is 5. So if we try to substitute the value for R, which is 100, so X here is equivalent to 2 meters. So now let us identify the maximum moment under 40 kilonewton. So if we're going to identify the maximum moment under the 40 kilonewton wheel, so let us draw the diagram. So we have here our beam. It has you have here R sub 1, you have here R sub 2. So this is 10, the span of the beam is 10 meters. So we have here, this will be our center line of the beam. So if this will be the center line, so we have to place our resultant in the 40 kilonewton in between the center lines. So we have here our resultant R. We have here our 40 kilonewton. Then this is our 60 kilonewton. So this is actually the distance. We have solved this X. This is our X, and this is equal to 2 meters. So therefore, if that is 2 meters, the span of this is 5. So therefore, this one is 3. So in the distance from the center line towards 40 kilonewton is 1.5. If that is 1.5, so basically this is 1.5. So since this is 5 towards this point, so 5 minus 1.5 is 3.5. So therefore, this is also 3.5. So now we have to identify our reaction at point 1. So to identify the reaction of point 1, so summation at R sub 2 is equal to 0. So therefore, if this is our reference point, so we have here in a clockwise direction, so you have R sub 1 times 10. Then we have our resultant force in a counterclockwise minus R multiplied to 3.5, and that is equal to 0. So this is R sub 1 times 10, then minus R is 100 times 3.5 equal to 0. So R sub 1 is equal to 35 kilonewton. So we have now the value for our R sub. Now let us identify the moment to the left of the 40 kilonewton. So if this is 40 kilonewton, to the left of that, we have our R sub 1. So this will be our reference point, which is at 40. So therefore, the moment to the left of 40 kilonewton is equal to, you have here R1 times the distance towards 40, which is 3.5. So this is 35 times 3.5. So it gives us 122.5 kilonewton meter. So maximum moment under 60 kilonewton wheel. So we have the beam. So this is our R sub 1. So we have our R sub 2. So this one is actually 10 meters. So basically this is 5. So you have here 5. So since we are going to compute for the maximum moment under 60 kilonewtons, so we have to place the center line in between our resultant and the 60 kilonewtons. So basically this is our center line. So if this is our center line, so this is our resultant, our R. So this will be our 60 kilonewton. So this distance actually is 2. So therefore this is 1. So this is 1. And the distance, since this is 5, so the distance from the resultant towards the R1 is 4. So this is actually equal to 4. And we still have our 40 kilonewton. So this distance is 3 meters. So basically, this is also equivalent to 4 meters. Now, for the maximum moment under the 60 kilonewton wheel, so let us have summation moment R sub 1 equal to 0. So we will have in a counterclockwise direction, so negative R sub 2 times 10. Then we have our resultant in a clockwise direction. So this is plus R times our moment arm distance, which is 4. So from the resultant towards our R1, that is 4 equal to 0. So therefore, our R is equal to, we have identified this one. So this is actually equal to 100. So R sub 2, therefore, is equal to 40 kilonewton. Now we have to identify the moment to the left of 60 kilonewton. So this will be to the left of 60 kilonewton, to the right, sorry, to the right of 60 kilonewton. So to the right of 60 kilonewton. So therefore, if that is to the right of 60 kilonewton, so we have here, this is 60 or R sub 2. So to the right of 60 kilonewton, so this will be our reference point. So we have R sub 2, so meaning to say you have R sub 2 times the moment arm distance, which is 4. So R sub 2 is 40 times 4, so this gives us 160 kilonewton meter. So we have now our moment to the right of 60 kilonewton from the under the 60 kilonewton wheel. From the previous 40 kilonewton wheel, that is only 125.5 kilonewton. So therefore, our maximum moment is equal to 160 kilonewton meter. So this is our maximum moment. So for this one, to compute now for the maximum shear, so maximum shear, it will occur when our biggest load, which is 60 kilonewton, is over the support. So for this one, if our 60 kilonewton is over the support, so meaning to say this is our R sub 2, so this will be our 60 kilonewton R sub 1. So we have our resultant R. So this distance is 2, so therefore this is 8. So therefore, we have summation moment R sub 1 equal to 0. So we can have R sub 2 times moment arm distance towards R sub 1, which is 10. Then in a clockwise direction, this is plus. Of course, this is counter, negative R sub 2 times 10. This is in a clockwise direction, R times 8. So this is equal to 0. So therefore, our R is 100. So solving for R sub 2, this is equal to 80 kilonewton. And therefore, our maximum shear is equal to 80 kilonewton. So that is for example number 1.